Hi, Martin. Okay, everything is in place. Hello, everybody. Uh, Thank you to everybody who's making it earlier than yesterday. This is very, very welcome for us starting this meeting at midnight in the past few days. And so today is only 9 o'clock, which is fantastic. Thank you again for your own effort to wake up early or go to bed late. So I have a short intro to the common envelope sections before we then introduce the speakers for the day. Okay, so let's go into screen sharing. I hope it's all working. Uh, okay, all good, Martin? It looks
Yes,
good from my
everything
side. Okay,
looks fine.
fantastic, thank you. So I'm at Macquarie University, and I'll introduce this session on common envelope interactions and the nebula they form. Of course, we speak here from Sydney on 4th month in lockdown, and when this number here turns to 80, which will be in 2 weeks, we get a little bit more freedom. It's been quite an exceptional time of our lives. This past 4 months is quite incredible. Anyway, aside from that, and not to digress, what is the common envelope interaction? So it's a little bit has been already discussed previously in this meeting, and we know that when two stars interact and the mass transfer that ensues is unstable, and the stars are in specific configurations of evolution, one star can be effectively engulfed by the other, and they go through a phase in spiral that happens on a dynamical timescale, and this can be timescales of days to months. The two stars in spiral, the orbit shortens greatly, and the envelope material that engulfs them both gets energized and acquires angular momentum, and it can be ejected. Now, if the binary survives, usually it's because most of the envelope has been ejected. If that doesn't happen, instead, the binary can then merge into one star. So the point here, though, is no matter, some mass is going to be ejected and will escape the system, and this may form a nebula in the future. Now here we have a simulation, one of the many recent simulations. This is from Luke, where we have the various time frames of the interaction taking place. And on the vertical axis, we see quite a lot of geometry taking place, which is very interesting for the formation of the nebula. Now, 3D hydro is kind of what we have used to understand this interaction because it's so rapid that we tend to not observe it in action. Today, this is not quite true because transients and the many surveys that are after time domain are really giving us a lot of data on things that we believe to be massive common envelope mergers. So we're starting really to see the thing in action. That said, in order to understand anything, you need a model, and here we go with 3D hydro. In the last 10 years, we've done a lot of things on top of the great pioneering work of the 70s and 80s. And what we do understand now is that is some of the details of when stars like RGB, AGB, and even more massive stars interact. I put massive in brackets to emphasize that's really the cutting edge at the moment. There are no real published simulations of massive stars, but they're just starting with 10 solar mass level stars. So most of my introduction will concentrate on lower mass stars, particularly AGB stars, but also RGB. We understand a little bit more about the energetics of the envelope. We are able to put the energy release when the envelope expands or recombines, and we're even able to eject and unbind envelopes, which until recently we were not doing quite so well. The problem in the simulations at the moment is that they are adiabatic, so they don't let go of anything. That means that the shapes that you see are poofy, they're not deflating thanks to cooling. That's what we were discussing with Guillermo on Monday. Also, it means that the recombination energy, which we're using and harnessing to do work and eject this envelope and make the nebula, actually might in part get radiated. If that's the case, then we're losing it. So we really need to get to radiating the common envelopes, but that's not happening yet. We don't convect, we don't produce dust, and dust, we all know in the AGB business, makes dust-driven winds, which are very important for the ejecta and the nebula that are formed. Now, as I said, we'll concentrate on lower mass stars and, of course, planetary nebulae. 1 in 5 of all planetary nebulae are ejected common envelopes. And this is a strict lower limit. This is what we know of, but there are lots and lots of observational biases that make us know that there's going to be a lot more than this. Now, the binary in the middle is a post-common envelope binary. It's called the central star, which is a white dwarf, and a companion, which is usually a low mass star, main sequence, or sometimes white dwarf. The nebula around are not as homogeneous as one might have expected from such a defined interaction, such as a common envelope. There's quite a lot of diversity. There's a lot of bipolarity. There's a lot of jets and collimations. And as you can see in the small little gallery, there's a lot of diversity. Now, we really ought to look at the nebula and be able to read off the nebula to know what happened 10,000 years ago when the common envelope that formed these nebulas took place. But we're not quite able to do that yet, but this is where the research is at the moment. You heard Guillermo's wonderful talk on Monday about how he converted the common envelope ejecta into a planetary nebula, doing what planetary nebulae do, which is blast this fast, thin wind on top of whatever was let go during the AGB, in which case, for us, is a common envelope. On the left, we have the structure that Guillermo used. It's a common envelope from a low mass star, taken 57 days after an spiral. So this is quite a small structure. Adam's group, in a couple of papers, took a much bigger structure, taken 15 years after the spiral, and did the same thing. We let the fast wind go inside to try and form the nebula. This is to put in perspective the two sizes. One is a small structure because it's very young. The other one is a little bit older and has had time to expand. As you blast this fast wind into this mold, we get, of course, lo and behold, some kind of bipolar ejection. What is great right now, on the one hand, these simulations are really early on. Guillermo has gone past this pure hydro simulations and done all kinds of things with magnetic fields and jets, as he explained on Monday. But the bottom line is this is the start of a big journey of mapping the nebula from the common envelope to the interaction that happened and the parameters of the stars in that interaction. Both these pictures are taken approximately 1,000 days. Sorry, I wrote 1,000 days after the blasting of the wind, and they're approximately to scale. So you see a lot of similarities. Lots of questions about cooling. As I said, we really need to put a lot more physics before we can start trusting fully, but this is a good beginning. Now, what about dust? We don't know anything about dust in common envelopes, but we do know that the opportunity for dust formation is right there. The dense environments and the low temperatures of the expanding common envelope are perfect dust formation sites, and we know from transients that dust does form readily in a matter of days in this expanding transients. So on here on the left, it's a density cut of a garden variety simulation, the same one that Adam used actually for the planetary nebula. On the right side is the equivalent map of opacity. In the middle, you have a lot of high opacity material. This is ionized electron scattering opacity. The black line is a recombination front, and outside of that, you have recombined material with very low opacity. However, as you can see outside the ring, you have orange again. That's high opacity due to molecules and dust. So we know dust is the opacity is there in the sense that the conditions in the gas are there for the formation of dust. And we'll hopefully soon we'll know a little bit more about this. Now, there's two more things I want to say as introduction before I let go the first speaker, and that is, what about the pre-planetary nebula and the post-AGB stars? Now, we talked about pre-planetary nebula on Monday. Again, Raghvendra gave a great talk. These are stars with nebula we believe to be the precursor of planetary nebula, but they seem to be a little bit different. They're always stunningly collimated, amazing objects, and we now believe that some kind of strong jet formation, binary interaction must have taken place. Now, Bruce Rivnak, for a lifetime, has looked to see if there's binaries in the middle of this. This would be the smoking gun of the interaction. However, he has not systematically found what we believe to be there. That would be some manner of post-common envelope compact binary. He has found instead that some of them are wide binaries, like 20, 30 year period. So the question is, if we still believe binarity to be critical to the formation of the nebula, as I do and many do, then this probably leads us to think this is going to be the result of a merger. Now, there's another type of star that in all ways is identical to the post-AGB stars in the middle of PPN. But these stars instead don't have any nebulosity, or they mostly don't have any nebulosity. And what they are, however, are all binaries, and they have circumbinary disks reconstructed here from a VLTI visibilities. And the binaries are periods of 100 to 2000 days. Now, 100 days is mighty close. They must have interacted strongly, even via common envelope, but somehow a common envelope that did not lead to the dramatic and spiral we are so familiar with. So what is going on in these stars, and why don't they make the nebulae? One idea about why they don't have nebulae readily is that they reaccrete disk material, and that stalls the evolution. They don't get hot, and they don't ionize the material before the material has time to move away. So the point here is we have an interesting group of objects and nebulae, and we're trying to construct a scenario. And I go with this scenario in my head. This comes from many, many, many papers in the literature, as well as my own experiences. And that is that the PPN are probably some kind of very strong binary interaction merger product, that the AGB common envelopes lead to post-AGB common envelopes, post-common envelope central stars or planetary nebula with very short binaries, that the wider binaries we find in post-AGB stars have gone through some kind of other mass transfer mechanism, but very, very strong, not your typical Roche lobe overflow, something that Noam has proposed as grazing envelope. The idea there is a very strong interaction that leads to this wider binaries, but has not quite done the tightening of the common envelope. And of course, there's a whole bunch of wider binaries that can influence the ejecta from the AGB and create nebulae nonetheless, and even with some interesting jets potentially, but not of the same type. So I'll leave you with this, and we'll see. We'll stop sharing. And is it stop sharing? Yes. Okay. And
Yes.
I think Martin, yes, all good. We can start with the first talk.